Today we would like to talk about the software testing. So firstly, let's do some recap. So in the lecture 15, we know what is the black box testing, white box testing, and the equivalent partition. The equivalent partition is just like what are the things that can't be. What kind of test it can be a class, one class or test. The system will have one response with this kind of a test, and the other one can be classified as another. The black box testing is just like we do not know what is within the system. We just throw them, and based on maybe the properties of the output. And the white box testing is just like we're going to know how the system is going to be built up, and through some specific edge cases for this program. Which means that we are going to design the program, we are going to design the test, derive the test cases based on the program. So coming up, we're going to talk about the pass testing, the cyclomatic complexity, integration testing, interface testing, and object-oriented testing. So firstly, pass testing is that do all roads really needed to run, which means that we are going to visualize how many roads do we have. It's to ensure every road is going to be at least executed at least once. So we must make sure that the set of test cases will reach to every possible state based on this road, and the program flow diagram shows up the nodes representing the program decision and arcs representing the flow of the control. The statement within the condition are therefore nodes within the flow graph. And the program flow graph describes the program flow, control flow. Each branch is shown as a separate graph. Loops are shown with the loops looping back to the loop. For example, this is one first three line, and the 6 and is the first L statement. This is the second L statement, and the final one is the final printing station, and basically some terminology for the graph. As j equals to v comma e, it's representing the whole graph. The number of verticals can be represented as the norm of v. The number of edges can be represented as the norm of e. So the number of e should be greater. Generally, the number of verticals is greater than the number of edges, just like this one illustrated here. And what if it's a fully connected graph? The number of edges with the number of nodes is the number of edges can be described as n times n minus 1 divided by 2, where n is the number of nodes. The cyclomatic complexity is the number of tests to test all control statements equal to the cyclomatic complexity. There are two ways to calculate. The first way is called the number of edges minus the number of vertices plus 2, and the second one is the number of conditions plus 1. So the conditions are any type of branching factors, and regarding the of the if, for, or while. It is useful only for with care. It does not imply the adequacy of testing. It executes all the passes, but not the adequacy of the passes. For example, in this case, we are going to do a binary search. So firstly, we start at the start of the program, and as the first while loop, what if it is less than? It's going to come to the end. What if it's smaller or equal to? And this is going to do the I think it's called the comparison. We're going to get the mid. And what if the mid is equals to the key, and we're going to return that key. Else we're going to else if it is less than the key, and it will re, uh, it will discard half of the searching elements, and it, it's worth noticing that this while loop, this while represents this 9 is the end of the search, and this while is the 8 here, and what if this 7 is the else here? Is this one after the conversion. This is the if, this is the else, and after conversion we go to the well, it is less than that. It's going to do that. What if it's not? It's going to go out of the while loop and going to this branch here, and to finally terminate this. So the columnatic complexity is both going to be 4 based on the calculation. There are some independent passes which are going to introduce new nodes to the test. For example, what if the pass is 1 to 8 9, and what if it can be there are some independent passes and be 1 2 3 8 9. It can also be 1 2 3 4 5 7 2 8 9. It can also be 1 2 3 4 5 6 7 8 2 9. That's first. And then we're going to talk about the integration testing. The integration testing tests the complex system or subsystem composed of integrated components. The integration testing should be a blackboard testing with the test derived from the specification. And integration testing has a main difficulty to localizing the errors. The incremental integration testing reduces this problem. So, for example, we are going to firstly test this kind of components, and then add another one which is C, and then add another one which is D. So we are gradually testing them. This is the thing that we are going to test as early as possible. That will be much beneficial because we can locate where the errors come from much easily. So the incremental integration testing, note that the incremental integration is, as the previous slide, is the idea of regression testing. The regression testing is that after you test the new components, you're going to test the original one, and but that means you're going to make sure the old component, which is the most important one, is good, and sometimes we can do task harness, which is the program written by automatic generator to test the data and record the result. There are several approaches to do the integration testing, which is top-down approach and bottom-up approach. With the top-down approach, mainly about just like the GUI, the user can can log on to the GUI and to see whether it allows this web page design or not. And bottom-up design is just like it's just like the normal class testing, where it's starting testing from the class and then subclass, and then this is the class and then subsystem and maybe system, something like that. And the bottom up is going to be used in the OP system and the real-time system, the system with strict performance and equivalent requirements. The reason why it's OP is obvious because it's originally a kind of class and method hierarchy, and the real-time system because we can identify the slow beats. Because we can identify the slow beats more quickly. because yeah, we can localize where the error comes from, and then the system with the strict performance and requirements mean because we can measure the performance of the individual method early in the testing process. The system performance required the system with strict. Yes, just like we are going to make the improvements in the future. Okay, and the testing approaches is mainly about architectural validation. It's just like the top-down understanding of whether it is valid or not. And the system decomposition just like allows limited decomposition in an early stage in the development. The test implementation is bottom-up integration, and the test observation is trying to observe how this test pass this testing. And that's all for today. Welcome for comments and subscription.